In this talk, I present some results obtained jointly with Olga Polverino and Ferdinando Zullo from my home university, and more recently with Marco Timpanella, who recently appointed at UCD in Dublin. I'm very happy for the nice talk of Giovanni before, also because he introduced many basics and many preliminaries that I'll make use of. So I'm very grateful to him. I'll start nevertheless with some...
I hope so. I hope so.
No, you did indeed. I'll start nevertheless with some preliminaries on rank metric codes, and then I'll focus on a specific family of codes for which we have obtained some results and some characterizations of the MRD property. Well, the ambient space is the FQ space of matrices, say m by n matrices over FQ, endowed with a rank distance, which has been described many times in these 2 days. A rank metric code is simply a metric subspace C, which is said to be linear if it is also an FQ subspace of the ambient space. The minimum distance is the minimum distance between 2 distinct code words, and being C linear, it equals the minimum rank of a non-zero code word. We'll denote in this way the parameters of such a linear rank metric code. These parameters obey this singleton-like bound, and when equality is attained in this bound, the code is said to be MRD, which stands for maximum rank distance, and is in a sense optimal. We focus on the square case, so m equals n, and in this case, as said by Giovanni before, we can look at the ambient space as the space of q polynomials over fq to the n with bounded degree under less than q to the n, with composition modulo the polynomial xq to the n minus x, defining the field fq to the n. Actually, basing on the fact that fq linear maps over fq to the n are uniquely described by q polynomials of this shape of bounded degree. So we'll look at codes in this ambient space. So the distance between 2 code words, between 2 maps f and g, is the rank of the difference as an FQ linear map. And also n minus the rank is the FQ dimension of the kernel, of course, as an FQ linear map. And the minimum distance of the code is the minimum rank of a non-zero map in C. Well, if C is not only FQ linear, but also FQn linear, that is closed under multiplication on the left by scalars in FQ to the n, we say that it is an FQn linear code. Well, consider an FQ to the n linear code in this ambient space. Okay, so that the dimension, the FQ dimension k, is n times the FQ to the n dimension, say h. The singleton-like bound then looks like this, and the code is MRD if and only if every non-zero code word has a FQ dimension of the kernel upper bounded by h minus 1. So focus on the case h equal 2, 2-dimensional FQ to the n linear codes, and consider the code generated by the identity x and another q polynomial, say f of x. This code C of f is MRD if and only if, as you can see above, the kernel of any non-zero code word, of any non-zero map inside this code, has FQ dimension at most 1. So, if you recall the talk by Giovanni, if and only if f is a scattered polynomial over FQ to the n. Well, actually, this is not just an example, but an important family. I'll try to say why in very few words. if the minimum distance is at least 2, then consider the left idealizer L of C, of the code C. That is the set of Q polynomials that composed on the left with a code word still provide a code word. This idealizer is a finite field of order at most Q to the n. Another definition, this is a natural actually, a definition of equivalence between rank metric codes in this ambient space. This is an equivalent and preserves all the interesting, from a coding theoretical point of view, properties of the codes. Well, the left idealizer is as an FQ algebra invariant under equivalence, and moreover, every FQ to the n linear MRD code with maximum left idealizer can be, up to equivalence, be written as C of f for some Q polynomial, for some scattered polynomial f of x. So this is a very important class to study, and actually it was studied because after some seminal, say, papers with the, say, most important classes of MRD codes, such as Gabidulin, generalized Gabidulin codes, and later twisting and generalized twisted Gabidulin codes, many families have been actually constructed in this way as two-dimensional FQ to the n linear MRD codes of the shape C of f. Okay. Please forgive me if I did not mention everyone, but it was actually not possible in this short piece of slide. But I'm particularly interested in a family introduced by Chaibok, Marino, Polverin, and Zanella a few years ago that can be described as follows. Take n to be even and delta a non-zero element of FQ to the n. And let S be a positive integer coprime with n half. And then define this polynomial, f delta S of x, which was already shown by Giovanni before. He investigated the partial scatteredness property of this polynomial f. We go directly to investigate the scattered property, say, that is the MRD property for the associated code. Well, what is known from this very first paper is that when the norm over FQ to the n half is not 1, then the weight, the FQ dimension of the kernel of any non-zero code word is at most 2. So either these codes are almost MRD, or if the kernel has always FQ dimension at most 1, this code is MRD. So this boosts the interest in investigating the MRD property for this code. Okay, what is known about the MRD properties for these codes? Well, firstly, it is very known that the property of being MRD does not really depend on delta, but rather on its norm, delta to the 1 plus q to the n half. Then the smallest case are very easy, because for n equal 2, this is MRD, being a Gabidulin code. For n equal 4, this code is MRD if and only if the norm of delta over FQ is not 1. And it is easily seen that such MRD codes are equivalent to twisted Gabidulin codes. Well, the first, say, difficult case is n equals 6. But indeed, this case is completely worked out by these two independent papers by Polverin and Zullo and Bartoli, Chaibok and Montanucci, which explicitly characterized, they give necessary and sufficient conditions for on delta for the code to be MRD, and also the exact number of such delta was computed. Well, for n equal 8, a sufficient condition for the MRD property is that the norm of delta is -1. But actually, the question is open, was open, say, whether this sufficient condition is also necessary. Not to say the case n greater than or equal to 10, for which nothing actually is known. Together with Olga and Ferdinando, we started by giving some arithmetic characterizations of the values of delta for which the code is MRD, and finally, totally skip the steps. We come up to this, say, arithmetic characterization. That is, the code is MRD if and only if there are no S, T, and Z in Fq to the n half, such that T is non-zero, and these two equations are satisfied. They depend on beta, that depends on the norm of delta, of course. Well, I put a bracket before and the letter X, because we can look at them, that equations, as affine equations defining an algebraic variety, defined over Fq to the n half. And then we can translate the MRD property into the non-existence of affine affine points with coordinates in Fq to the n half of this variety X. And then we applied the, say, algebraic geometry machinery. In particular, we were able to show that this variety has dimension 1, it is a curve, and it is absolutely reducible. And we explicitly computed the genus. With these ingredients, we could apply the Hasse-Weil lower bound on the number of rational points, and which is stated on the slide here, very elegant and concise, as you can see. Well, when n is big enough with respect to the genus, that is with respect to S, this number, capital N, is positive and big enough to ensure the existence of suitable rational affine points, so that the code is not MRD. Well, for even Q, when Q is an even prime part, the arithmetic characterizations were different, but still the procedure was that of obtaining a rational absolutely reducible curve defined over Fq to the n half, and to ensure the existence of suitable affine Fq to the n half rational points. Summing the odd and even cases together, we ended up with this result that states that when n is big enough with respect to S, then the code for any non-zero delta, the code is not MRD. So this is, for n at least 10, this is a very different situation from the cases n equals 6 and n equals 8, when we actually had MRD codes in this family. Note that when S equals 1, it is enough to take n greater than or equal to 10. So for S equal 1, the larger n from 10 on are completely worked out. Well, what about the remaining case for a smaller n? In particular, can we give not just sufficient but necessary and sufficient conditions for the MRD properties in the case n equal 8? With Marco Timpanella, we tried to address this problem. Let me just recall that the norm of delta being equal to -1 is a sufficient condition for the code to be MRD, and numerical evidence by these authors suggests that this condition might also be necessary. For larger Q, well, we can restrict to the case S equal 1. The MRD property does not really depend on S. And the point already noticed with Olga and Ferdinando is that the curve studied before is no longer enough to apply effectively a severe lower bound. Why? Because the genus, that is actually the degree of this curve, is too high with respect to the order of the field. Okay, so our goal was to translate the MRD property into a new algebraic variety, a different algebraic variety, with low degree, in particular with fixed degree, so that when Q grows, the degree is small enough with respect to order of the field, and we can apply an Aceveil type lower bound, which for higher dimension is named after Lang and Weil. Well, briefly, what we did. Well, we write the coordinates s and z on a normal basis of Fq to the 4 over Fq, so that when s and z are in Fq to the 4, Si and Zi are in Fq. And we connect the Fq to the 4 rational points of X with the Fq rational points of an algebraic variety, say W, in the homogeneous coordinates Si and Zi. So this variety is embedded in a 7-dimensional projective space. It is Fq rational, and it is 3-dimensional and of degree 16. So one may guess to prove, for instance, absolute irreducibility of W and application of Lang-Weil. Well, actually, this turns out not to be true even, but this procedure cannot be handled in practice because of the equations of W. So we give new variables, which are the consecutive Q powers of S and Z. And starting from the equation of X, we obtain an explicit and easier to handle algebraic variety V in the homogeneous coordinates Xi and Yi, which is Fq to the 4 projectively equivalent to W. And projected, and not just birational in general, equivalence means that also the degree of an absolutely reducible component is preserved. And this is useful at the end for the concrete application of the bounds. Well, this is just to let you see the rapid glance at the equations of this variety. Well, with much help of magma and of some algebraic geometric arguments, we were able to find for all values of delta and hence of beta under investigation an absolutely irreducible component of B, which is the only one having its dimension and its degree, so that the corresponding component of W must be, for sure, defined over Fq, even though we do not know it, this component of W, explicitly. And the nicer thing is that V is not absolutely reducible in general, and depending on the value of beta, we have 1 or 3 components of maximal dimension with different degrees. But these things allow us.
2 minutes.
Okay, I'm ready. I'm really finishing. This allows us to apply Lang-Weil bound to this component and to conclude that for Q odd and big enough, unfortunately, we cannot avoid this assumption because of the algebraic geometric techniques that we use. We are able to say that for n equal 8, Q odd and big enough, the MRD codes C delta S are only the ones where the norm of delta equals -1, so that we gave a partial classification of MRD. Yeah, I can maybe say that one may easily notice that there is still an open case also for large Q, that is when Q is even. This is because actually we tried to apply a similar argument, but the technical difficulties with the varieties that come up, okay, are still too difficult to us. We were not able to come to an end. But this is always I wanted to say. Thank you for your attention.